3. Cloud chamber tracks. Nuclear radiation is invisible. However, we can trace their tracks and identify them using a diffusion cloud chamber. When an ionizing radiation such as alpha radiation travels across a diffusion cloud chamber, it produces many ion pairs along its path. A cloud chamber is filled with supersaturated alcohol vapor. Due to electrostatic attractions of charged ions, the vapor molecules will readily condense on the ions. The alcohol droplets formed will reflect light and appear as bright spots to form a white track. Take a look of the experiment to see how a diffusion cloud chamber is prepared and what the tracks look like.
We are going to observe the tracks of alpha particles in a diffusion cloud chamber. This is a diffusion cloud chamber. Put some dry ice in its lower part. Cover the dry ice with a foam pad and screw the base lid back on. Use a dropper to add some methylated spirit to the felt ring in the upper part of the chamber. Replace the plastic lid. Illuminate the chamber with a lamp. Insert a weak radium source into the chamber and observe from above the tracks produced. Now, rotate the source so that it is behind the tin foil inside the chamber. Is there any change in the tracks produced?
From the video, we can find that the tracks are formed randomly. Random in time when they are formed and also random in their directions. Some tracks are thicker while some are thinner, some are straight while some are curvy. It depends on the type of radiation used. Tracks are also random in their lengths, and the length of track depends on the energy of the radiation. Alpha tracks are thick and straight, which means alpha radiation can travel undeflected and produce a lot of ion pairs along its track. The tracks usually have different lengths, which means the alpha radiation have different energies. Alpha particles are comparatively massive, and so it may travel in straight line. Its ionizing power is strong, and so a lot of ion pairs are produced along its path. Beta tracks are scattered tracks. They are short and curvy, which means beta radiation can hardly travel in straight line, and their ionizing power is also weak, producing just a few ion pairs along its path. Beta particles are electrons. They are easily deflected, and so they can hardly travel in straight line. Gamma tracks are difficult to observe, as their ionizing power is the weakest. Instead of filling the chamber with air and alcohol vapor, scientists also try to fill the chamber with helium and alcohol vapor. It happens that an alpha particle collides with a helium atom to produce a right-angle fork, as shown in figure 1.2k below.
The apparatus as shown is used to simulate particle collision. First, we spray the plastic beans over the tray. We are going to use the pair of magnets with identical mass to simulate the collision between two particles with the same mass. Push one magnetic puck gently to collide at an angle with the other one, which is stationary. What can you notice about the angle between the tracks of the magnets? Now we use a pair of pucks of different mass and repeat the experiment to simulate the collision between two particles of different mass. What happens if the colliding pucks have different mass?
From the right-angle fork, physicists deduced that our particle has the same mass as a helium atom. Since it has a strong ionizing power, physicists also find that its charge is positive 2 units. They conclude that our radiation is in fact a stream of helium nuclei. Do check point 2 below.